All right, welcome back. So we're approaching the end. We have two more chapters to do. Excretory system, that will start today, which is under the larger title of osmoregulation. And then the second chapter is the immunology chapter. All right, so osmoregulation. All right, so the physiological systems of animals, from cells to tissues to organs and organ systems, as well as the organism, operate within a fluid environment. Right? I mean, we don't live in water, right? We're terrestrial organisms, but our cells are bathed in water, and because tissues are made of cells and organs are made of tissues, and organ systems are made of organs, and we are made of organ systems, really, we're in a fluid environment, both an intracellular fluid environment and an extracellular fluid environment. Okay? All right, for these fluid environments to operate properly, they often must be maintained within very narrow limits. So we could think about concentration of ions, in particular maybe the concentration of hydrogen ions, which relates directly to the pH of the cell. And this fluid environment is often having to be maintained in the face of particular challenges in the environment. Now, we talked a little bit about this in the homeostasis chapter, the idea that often there are fluctuations in the external environment, and we're trying to keep these internal environment fluctuations much smaller. It's homeostasis. Well, osmoregulation is one of those ways that we can maintain homeostasis. So it makes sense that when we talk about osmoregulation, homeostasis, that discussion bleeds into it. Okay? All right. So yeah, let's go ahead and go into this. All right, so when we think about this fluid environment and we think of kind of osmoregulation, immediately what should occur to you is something to do with salt balance. Whether we're talking about concentration of sodium ions or concentration of potassium ions, all of these inorganic salts are being maintained at particular concentrations in cells and in extracellular fluid. So often when we talk about osmoregulation, we're talking about some sort of inherent salt balance. At the same time, we're going to be dealing with salt balance. We're also going to have to deal with kind of the products of metabolism. Usually when we talk about products of metabolism, we're talking about things that are constructed, but here I'm talking about things that are being produced as a consequence of metabolism that we really don't want hanging around. So in some sense, these are byproducts of metabolism. We aren't directly setting out to produce these. They're being produced as a consequence of trying to produce what we want to make. And these metabolic wastes are being produced. The main one that we're going to talk about is a byproduct of nitrogen metabolism, in particular protein metabolism and nucleic acid metabolism. And the problem is when these break down, when these break down, and everything breaks down at some point, trust me, the breakdown of proteins and nucleic acids, we do get a main breakdown product. And that's the main breakdown product of protein and nucleic acids. It yields this molecule called ammonia. Ammonia can exist in a couple of different forms. The main one, I just want to check my math here, is NH3. And then you can also get the formation of ammonium which is NH4 plus. But in any event, ammonia is not a nice molecule. There's no accident that it's used as a cleaner, right, to remove organisms from your tub, tile, or shower. Ammonia is highly toxic. Okay, so this should, as by way of an introduction here, lead us to two main concepts. When we talk about osmoregulation, we're really talking about two things happening kind of at the same time. The first is regulation of salt concentration and water concentration. Right. Regulation of salts and water concentration. That's what we'll call osmoregulation. And then the second piece of this happens as a consequence of the regulation of salts, plus trying to rid yourself of these waste products of metabolism. We're going to call that excretion. Okay, excretion. Here's the removal and ridding yourself, I guess, what we'll call nitrogenous waste. Nitrogenous waste is a catch-all category for things like ammonia, plus what ammonia can be converted to in different animals. Okay? All right, sounds so good so far? So the osmoregulation chapter is really about two things. Osmoregulation, the regulation of salt concentration, and water concentration, which we'll call salt balance, and excretion, which is the removal of these naturally occurring byproducts of metabolism. All right. Now, this is extracellular fluid. Here is a cell here. And I just want to recall that we can get water to enter or leave cells. The water is entering or leaving cells primarily due to differences in concentration. Osmosis. It's going to be one of those days, I can feel it already. The sun's out, it's a very nice day, and my mind is looking out the window. All right, so what's regulating the movement of water in and out of cells is essentially osmosis, which is driven by differences in concentration. Differences in the concentration of water. But recall that we don't often think about water concentration when we think about water moving. In fact, the language that we tend to use to describe solutions of water is not related to the concentration of water itself, but rather to the concentration of salts. So here's two compartments here separated by some sort of a semi-permeable membrane. In this case, let's make it impervious to the movement of salts, but water can pass back and forth. If I set up a large concentration of salts here, that would make this hypertonic, and this then would be hypotonic in reference to the concentration of salts. This solution has a higher concentration of salts than this solution, and this solution has a lower concentration of salts than that solution. But if we're talking about osmosis, we're talking about differences in water concentration. So what I often tell people in MCB is that unfortunately the language is kind of screwy because the salt can't move but the water can, and osmosis is driven by differences in concentration of water. We need to figure out which side has the higher concentration of water. And over here, hyper means over and above or in excess. Tonic is salt. So this is excess of salts. What that really means is that it's a low concentration of water. Here, hypo, lower, tonic salt, lower salt concentration. What this really means is that we have a high concentration of water. So we can predict the movement of water based on the concentration of salts. Low concentration of salts is high water. That suggests that the net movement of water will be from hypotonic to hypertonic solutions. Okay? Now, the physiology people, they don't tend to use the hypo and hypertonic language. Instead, what they're going to use is language that's related to the concentration of substances that are osmotically active. This concept is osmolarity. So inside my cell, I do have salts. I would expect there to be a certain concentration of calcium ions, hydrogen ions, sodium ions, potassium ions, chloride ions, manganese, magnesium ions, etc., etc. All these different ions. And these ions have the ability to take up space that water would normally take up, right? And therefore, these affect the concentration of water. Furthermore, because these are ions and they're charged, the water is going to want to form hydration spheres around these molecules, and these molecules can lock water up and make it unavailable to do work. But we don't just have to consider things like inorganic salts, right? This terminology is related to salt. We could also think about other substances that are charged, but we really don't think of them as salts. So proteins have charges on them, right? Positive, negative. They're hydrophobic, R groups as well, but there are regions of charge on proteins. Nucleic acids have all those negative charges on them related to those phosphate groups as part of the sugar phosphate backbone. Those also have the ability to hold water as hydration spheres, but they're also displacing the water and affecting the concentration of water. So this new concept here is really thinking about the concentration of osmotically active substances, which means substances that affect osmosis by altering concentrations of water molecules and by affecting their ability to move. Okay? All right. If we talked about concentration of these osmotically active substances, we could talk about an osmole. Okay? 1 osmole is 1 mole of solute, right, where the solute has the ability to affect water. Okay? Right, so in just between you and me, I mean, I could think of 1 mole of sodium chloride, right? This is going to become 2 osmole of osmotically active substances, 1 mole of sodium ions and 1 mole of chloride ions equals 2 osmoles, right? 2 moles of osmotically active substances. All right, if the osmolarity is equal between 2 substances, we say that the 2 solutions are isoosmotic, kind of like isotonic isoosmotic. And if the two solutions differ, one has to be hypoosmotic and the other would be hyperosmotic. Okay? And then water would move from a hypoosmotic substance toward a hyperosmotic, because the hyperosmotic contains more of these osmotically active substances. High concentration of water, low concentration of water. Water moves down its own concentration gradient. Okay? All right. I noticed, I think my slides here were a little out of sequence, but I'm gonna work with them, and of course you've got a copy of them that you can work with too. Let's lay out some terminology before we get into these osmoregulatory expiratory systems. Let's just lay out some basic terminology, or continue to, as we move along here. So, some organisms are going to be isoosmotic to their environment. And the interesting one to talk about would be an organism that's isoosmotic to seawater. Okay? That means that the organism, let's take this little sea star here, and then here's the seawater that it's in. This organism is isoosmotic. That means that the organism itself really doesn't do any of this osmoregulation, right? In a sense, as the seawater concentrations change, right? Maybe I'm right next to the runoff from a river, so the salt concentration is being diluted out. This sea star's internal concentration of water follows whatever happens in the ocean. So we say that this kind of an organism is a conformer. I think we used that language in the previous chapter on homeostasis. And because this organism is conforming with respect to seawater,